partial differential equations. We have derived it. And these four partial differential equations which we have derived in the previous session, we call them as Maxwell's relations. So we will continue with what we have left out. So the next topic is the TDS equations. TDS equations, we have already learned two TDS equations already when we talked about entropy, and now we will deal with TDS equations which can be derived from those equations also, but now let's look at it from another point of view. Okay, so it would be better if you take a pen and paper or pen and notebook and just start writing as, or you can just note it down as we move on. Okay, so let's say our entropy is a function of temperature and volume only. Okay, if entropy depends on temperature and volume, then we can write a small change in S, ds, in terms of partial differential equations. And in max, we write this as partial S, partial T at constant V into dt. Plus partial S, partial V at constant T into dV. Okay, this is a way of representing S as a function of T and V. So ds, it can be written like this. And because we are interested in TDS equation, we can multiply with T everywhere so that it becomes a TDS equation. So you multiply with T with every term in the equation. So you get T times partial S, partial T at constant V into dt plus T times partial S, partial V at constant T times dV. Okay, and so let's hold on to this equation. Maybe we can call this equation as A. Okay, and let's go to the first law, where we can say the first law tells us dq is du plus dw. Okay, and we can write this dq as TDS. And we can write this du as Cv times dt. And we can write this dw as pdv. Okay, for a constant volume process. So if you are taking a constant volume process, if I write this as for a constant volume process, so you know that if the volume is going to be constant, then dV is going to be 0. So this term will vanish for a constant volume process. So you can write your TdS is equal to Cv times dt, or I can write this as ds by dt, and I have a t here which can be written as Cv. Okay, and the same equation I can also write this as t times partial s partial t at constant v, and this is equal to Cv. So when I wrote here my entropy is a function of temperature only. So now, so it is a simple differential equation. Now what I do is I have said the volume is constant. So if S is a function of T and V, then I can convert this differential equation into a partial differential equation. Both of them are one and the same. And what is the advantage of having this is this particular term, T times partial S partial T at constant V, is there in this equation A. Okay, so I can replace this entire term with Cv. So your equation A becomes TdS is equal to Cv times dt plus T times partial S partial V at constant T into dV. So this equation is called as, we can further simplify this. See, here you have got partial S partial V at constant T. If we can see partial S partial V at constant T, the third Maxwell relation, partial S partial V at constant T can be replaced by partial T at constant V. So from third Maxwell relation, you can replace dou S by dou V with dou P by dou T, partial P partial T. So this equation can be written as, so TdS equal to Cv times dt plus T times partial P partial T at constant V into T. And this equation is called as the first TdS equation. Okay, so Cv dt plus T times partial P partial T at constant V into dV. In a similar fashion, you can also derive another TdS equation by taking S as, or entropy as, a function of temperature and pressure. You can follow the same steps. You can follow the same steps. So you can write ds. So if you have got a note and pen, you can try it. You can just, as I write, you can try it on your own. Partial S partial T at constant P into dt plus partial S partial P at constant T into dt. Okay, and just like we wrote here, I can write, you can multiply with TdS everywhere. You can multiply with T everywhere. So you will get TdS is equal to T times partial S partial T at constant P into dt plus T times partial S partial P at constant T into dp. Okay. And just like we replace this T times partial S partial T at constant P into dt, see this T times partial S partial T at constant P can also be replaced with Cp. Okay. And the same way you can do that. You can write dq is du plus dw. So what you have is TdS equal to du plus PdV. And if you remember, we can replace this PdV with d of PV is PdV plus VdP. So PdV can be written as d of PV minus VdP. So we can write this as d of PV minus VdP. And you can combine the differential terms. These two you can write this as d of U plus PV. This we have already done when we derived Maxwell's relation. So this is actually a repetition only. D of U plus PV minus VdP. So that is nothing but dH minus VdP.
So the thing written in the bottom isn't visible, sir.
Okay, I'll take the next one.
Yes.
So what I have written is TdS, that is equal to d of U plus PV minus VdP. And you know U plus PV is dH. So this becomes dH minus VdP. And for a process where your pressure is held constant, which is an isobaric process. So for a process P equal to constant, okay, so this term will vanish. Okay, so which means what you have is TdS equal to dH, and dH can be written as Cp times dt. So just like we did there, we can write this as T times ds by dt equal to Cp. And the same equation, I can write this as T times partial S partial T at constant P equal to Cp. Okay. So now I can write, so what we had before was TdS equal to T times partial S partial T at constant P into dt. This was the first term. And the second term was T times partial S partial P at constant T into dt. Now I'm going to replace this term with Cp. So what we have is TdS is equal to Cp times dt. And now we have to replace this partial S partial P at constant C. So let's see which Maxwell relation holds good for that. Partial S partial P at constant P. So that is Maxwell relation 4. And there is a negative sign, so that can be taken to the other side. So we should replace partial S partial P at constant P with partial V partial T at constant P. Okay. So we have a minus sign and we have a T term here, partial V partial T at constant P, and this should be dP and multiplied by T. So this equation is called as the second TdS equation. So we have one TdS equation in terms of Cp. We have another TdS equation in terms of Cv. So these two equations we will use. What is the use of having these two equations? From that, we will be able to get the difference in heat capacities. So if you look at it, I have used capital H. Capital H is enthalpy. And so this is capital Cp. This is not specific heat. So this capital Cp is heat capacity at constant pressure, which is nothing but mass multiplied by small Cp, specific heat at constant pressure. So mass into specific heat at constant pressure will give you the heat capacity at constant pressure. Okay. So this capital, so what we have here is heat capacity and not specific heat. So that is something which you should note it down. Okay. So now we have got two equations. One equation in terms of Cv, the other equation in terms of Cp. So what are those two equations? One is TdS equals Cv times dt plus,
So here also CV is capital.
yeah, it's capital.
Yes.
T times partial P partial T at constant V into dV. So this is number one. And number two, what we have is TdS equal to Cp times dt. This is also capital Cp Cp times dt minus T times partial V partial T at constant P into dP. Okay, we have got these two equations, equation 1 and equation 2. If you look at equation 1 and equation 2, the left hand sides are equal, which means the right hand sides are also supposed to be equal. So what you have is you can equate these two. You can equate these two equations. So you get Cv times dt plus T times partial P partial T at constant V into dV. This is equal to Cp times dt minus T times partial V partial T at constant P into dt. Okay, so I can equate this. So if I rearrange the term, what I'll have is Cp minus Cv, because both of them are having this dt as common. So Cp minus Cv times dt, this is equal to, so Cv is brought to this side and this fellow is brought to the other side. So this has T times partial P partial T at constant V into dV plus T times partial V partial T at constant P. So if you are just looking at this lecture, you won't get anything. Only if you write it side by side, you will be able to get something, or you will be able to get understand something. Okay. So now what I can do is I can just retain dt on one side, and I can write this as t times partial p partial t at constant v into dv divided by Cp minus Cv plus T times partial V partial T at constant P times dB whole divided by Cp minus C. So let's just have that equation separately. And if I take temperature as a function of pressure and volume, you can write dT as partial T partial P at constant V into dP plus partial T partial V at constant P into dV. You can compare these two equations. Say if you take this as equation 1, and if you take this as equation number 2, see the left hand sides are equal, so you can equate the right hand sides. And in the right hand side, what you can find is you have a term with dV and you have a term with dP. The same happens here. You have a term with dV and you have a term with dP. So if you equate it, you can also equate the coefficient of that term. Okay, so the coefficient of dV, you can equate it on both sides. So you can say by comparing 1 and 2, so comparing So comparing 1 and 2, what we find is partial T by partial V at constant P. This is equal to T times partial P partial T at constant V into dV whole divided by Cp minus Cv.
So the dp term,
Yes? Sorry, yeah. You won't have the dV term. Yeah, you're right. We are just comparing, so you won't have the dV term. You're right. Okay. So now I can also rearrange this and write this as Cp minus Cv is just T times partial P partial T at constant V multiplied by partial T partial V. Sorry, it should be, sorry about that. This should be V partial V divided by partial T. Sorry about that, guys. Partial V by partial T at constant, because we are cross multiplying, right? Okay, so this is brought over here. So this should come in the denominator. So we are inverting the term. So it should be partial V partial T at constant. Okay, so up to this, it should be okay for you. And now I'm going to show you one more result. Okay, and we are not going to see the proof of it, but uh, you need that for so what we can do is, say suppose I have three terms, x, y, and z. I have three terms, three variables, and these three variables are we usually represent them like this, like a cycle we can do. What is this is nothing but, if you write them in terms of differential equation, you can write this as partial x partial y at constant z multiplied by partial y partial z at constant x. multiplied by partial z partial x at constant y, this is equal to -1. This is a mathematical result. The proof of it is available in Thermodynamics by PK Nath. So if you are interested, you can go and look at that proof. You can try solving them at also. It is worth solving it. Okay. So just in place of x, y, z, I can write it in terms of pressure, volume, and temperature. PVT. So just like I wrote x, y, z, I can write it in terms of pressure, volume, and temperature. So like a cycle I can have, and we can write this as partial P, partial V at constant T multiplied by partial V, partial T at constant P multiplied by partial T, partial P at constant V is equal to -1. So if you look at the previous relation, what we have here is P times partial P partial T at constant P multiplied by partial V partial T at constant P. Okay. So what we can do is we can write partial P partial T. So here I can write this as partial P partial T, which means I am taking it to the other side. Partial P partial T at constant V is equal to minus of partial P partial V at constant T into partial V partial T at constant. So I can replace this term. So what we have actually got in the previous slide is we have got the equation Cp minus Cv equal to T times partial P partial T at constant V multiplied by partial V partial T at constant V. So now I'm going to replace partial P partial T at constant V in this particular equation with this relation. So if I replace or if I substitute for partial T at constant V, what I'll have is minus T. Okay, I have one term partial V at constant T. So there is one term partial P partial V at constant T, and the other term partial V by partial T is already present, so it will be a square term. So partial V by partial T at constant P, the whole squared. So this is what we get for the difference in heat capacity. So the difference in heat capacities, we are getting Cp minus Cv as minus t partial t the whole squared at constant t multiplied by partial v at constant t. So this is the relation that we get for your difference in specific heat capacities. Okay. So now from this particular equation, Cp minus Cv equal to minus T partial t at constant T the whole squared multiplied by partial v at constant T, we can have some inferences. Okay. The first inference is number one. So if you look at this particular equation, okay, this term partial V by partial T, the term partial V by partial T, be it negative or positive, because there is a square, this whole term, the first term together makes it a positive term. Partial v by partial t, the whole squared is positive. Because anything, a minus, a negative number to the power raised to the power 2 will give you a positive number. Okay, so this term partial v by partial t, the whole squared, that is going to be positive. Okay, we know that Cp minus Cv is positive. Okay, but you have a negative sign here. Temperature is never going to be negative. So which means this partial p by partial v for constant t, this is supposed to be negative. So this term partial p by partial v is supposed to be negative. Okay. So in a PV diagram, partial p by partial v is nothing but a negative slope. Okay. So if we are having a negative slope, partial p by partial v, so you're in a PV diagram, negative slope you have when for Cp minus Cv. Okay. So this also shows that Cp is always greater than Cv. The second inference, what you can see here is, see if your temperature, if it tends to 0 Kelvin, if your temperature becomes 0, what will happen to the right hand side? Everything will become 0 because it is just products. So if your temperature tends to 0 Kelvin, your Cp minus Cv is equal to 0, which means Cp is equal to Cv. That is the second difference. So if your temperature tends to 0, that is at absolute 0, your Cp value is equal to Cv. Okay. Another inference what we can see here is partial V partial T. If this becomes 0, so this is in a VT diagram, a diagram with volume on the y-axis and temperature on the x-axis. So if that is the case, when you have a maximum, in that particular VT plate, so the condition for maxima is what is the condition for maxima? Where do you get the maxima or the minima? What is the mathematical condition for it?
Double differential will be negative for maxima and positive for minima.
Okay, what about the first the derivative of the first order? The first order derivative will be equal to 0. So the condition for maxima is usually the first order derivative will be equal to 0, right? So when density is maximum, we can say partial V partial T is equal to 0. Density is mass by volume, right? So one condition for maximum density is partial V by partial T is equal to 0. So in such case, once again, your Cp will be equal to Cv. So your Cp will be equal to Cv when T tends to 0, or your Cp will be equal to Cv when partial V by partial T is also equal to 0. A normal rule for estimating maxima or minima in a curve is the first order derivative is equated to 0. Then for additional conditions, what you said is also applicable. Okay. Then for an ideal gas, okay, an ideal gas is something which follows the relation PV is equal to MRT. Okay. So if it is an ideal gas, then we have two partial differential terms in the equation for Cp minus Cv. One is partial d by partial t. So if you differentiate this, so if you say, if you want to find the dV by dt here, so P dV equal to Mr dt. If you are differentiating, so you can write dV by dt is equal to, because what we require is dV by dt, I am just differentiating volume on the left hand side and differentiating temperature on the right hand side. So dV by dt will give you R by P, mR by P, let me say mR by P, okay. And mR by P can also be written as from the first equation. If you have mR by P, what is left out is capital V divided by T, volume divided by temperature, right? So you have volume divided by temperature. What is the next term? Partial P, partial V. So what I require is dP by dV, okay. So how do you get dP by dV? Partial P by partial V at constant T. Okay, so what you can write is, say suppose I have P equal to mRT by V, and if I differentiate this by keeping the rest constant, dP is equal to mRT, no disturbance, and 1 by V, if you differentiate it, what you'll have is minus 1 by V squared times dV. So what we require is dP by dV. So dP by dV equal to minus mRT divided by V squared. And if you just have mRT by V, mRT by V is nothing but pressure P. So that is nothing but minus of P divided by V. Okay. So now if we substitute that in this particular equation, so what you'll have is Cp minus Cv. Let's see which one is appropriate to substitute. So we have minus T multiplied by V squared by T squared. And so I think we can substitute with minus mRT by V squared directly. So this is within the brackets, minus mRT by V squared, because we have a V squared in the numerator, so it is easy to cancel. So I'm just substituting mRT by V squared directly. So V squared and V squared we can cancel. This T and T in the numerator becomes T squared, and this T squared can also be cancelled. And minus into minus will be plus. So Cp minus Cv is M into R, which is absolutely right. And this is what we have been using in all our problems before. We always use Cp minus Cv equal to R, because this is heat capacity. M times Cp minus M times small cv, it has given you M times R. So Cp minus Cv as heat capacity is Mr. If it has small Cp, so if it has small Cp minus small Cv, that is simply R. If it is capital Cp minus capital Cd, that is going to be mass multiplied by R. So this is for an ideal gas. Okay. So these are the four inferences that we get. So the first inference tells us because partial d by partial t the whole squared is positive, partial b by partial v should be negative. That makes Cp minus Cv positive and Cp is always greater than Cv. That is inference one. Number two, when temperature tends to 0 Kelvin, your Cp is equal to Cv. When partial p by partial v, when partial v by partial t is equal to 0, which is the condition for maximum density, Cp is equal to Cv. Then for an ideal gas, we find Cp minus Cv is equal to m times R. These are some of the inferences. Okay. Now, I just want you to listen a little bit carefully because we are going to define something. Okay. I'm going to introduce a term called volume expansivity. I'm going to introduce a term called volume expansivity. Expansion of volume. So volume expansivity. Okay. And I'm going to denote this in terms of beta. And I'm defining this as 1 by V partial V partial T at constant P. So I define volume expansivity beta as 1 by V partial T at constant P. Okay, so keep that in mind. So this definition is something which you should remember. Similarly, I'm also going to, all these definitions are interrelated, so it will be easy for you to remember. If you just have one in your memory, the rest are easy to remember. I also have a term called isothermal compressibility. I have a term called isothermal compressibility. Okay, and this is denoted as, sorry, not beta. This is denoted in terms of K suffix T. Okay, K suffix T is isothermal compressibility, and this is defined as 1 by V with a minus before, minus 1 by V partial V partial P at constant T. Okay, these two definitions I want you to remember. One is 1 by V partial T at constant P, which is your beta, and the other one is minus 1 by V partial P at constant T. Okay, if we come back to this particular equation, Cp minus Cv equal to minus T partial T at constant T the whole squared. Okay, and partial P at constant T. So we have these two equations. Okay, and if you look at this volume expansivity, I have a term partial T at constant P. Okay, so I have here partial T at constant P raised to the power 2. Okay, what is missing is 1 by V. Okay, so I can multiply and divide by this volume. Okay, so I can multiply and divide by volume here so that I can express this in terms of beta. Similarly, what you have is partial V, and here we have partial P. What is missing is this volume. Okay, so Um, let me try and use another color. So Cp minus Cv, no change on the left hand side. So what I require is 1 by V the whole squared, because this is a square term. Okay. So what we have is V squared multiplied by 1 by V partial V partial T the whole squared. So that doesn't violate anything. I have multiplied by V squared, and this is V to the power 2. So these two can be cancelled. And I'll simply have partial V partial T at constant P the whole square. Okay. So, and this partial P by partial V we have. Okay. So here it is minus 1 by V. So what we do is we multiply with V and divide it by V. Okay. So what we do here is V times partial P partial V at constant T, and to compensate for this V, we are dividing it by a V. Okay. And now for this term, what you have is beta squared. And for this, there is a minus. So it is, you already have a minus here. So this is minus of 1 by AT. Okay. And you have one volume, and here there is a volume squared, so I can cancel out one term. So what you have is minus TV here, and there is a minus inside this braces, so you can take multiply that, and what you have here is TV beta squared. So this is beta squared divided by AT. Okay, we are not studying the significance of this, but sometimes they ask you to prove this. Maybe for a 11-mark question, they ask you to start from the TDS equation. So starting from TDS equations, prove Cp minus Cv is equal to Td beta squared by Kt. So if they are asking you to prove this, then this is the steps by which you can get here. Okay, and for that you just need to remember the definition of volume expansivity and isothermal compressibility, beta and Kp. Okay, so you can't just observe this and comprehend it. You need to write it down and make sure that you know the steps by which this particular result is obtained. Unless or otherwise you practice it, it won't be easy for you. Okay, so let's move on to the next topic, which is ratio of specific heat capacities. Okay, so here once again we have to use those two TDS equations. So what are those two TDS equations? So we said TDS is equal to CV times dt plus T times partial P partial T at constant V into dV. Okay, And the other equation is TdS is equal to Cp times dt minus T times partial V partial T at constant P into dP. Okay, these are the two TdS equations. Okay, now what we are saying is, if I have a constant entropy process, okay, so at S equal to constant, at S equal to constant, ds will be equal to 0, which means the left hand side will vanish. So this will become 0. Both of them will become 0. So what you will have is Cv dt is simply minus T times partial P partial T at constant V into dV. So this is for Cv dt. And similarly, you can also write Cp dt as T times partial V partial T at constant P into dP. Okay, so I have got these two. So now what we require is ratio of specific heat capacity. So I hope now you are able to understand what I'm going to do. So what we require is Cp by Cv. So if I call this as equation 1 and if I call this as equation number 2, so now what I'm doing is 2 divided by 1. That is what I'm doing. So Cp by Cv will be equal to T times partial V partial T at constant P into dP, and there is a negative sign in the denominator, so let's take that as common. T times partial P, the negative sign is actually in the denominator. I have taken that as common, so don't be confused. There is no denominator, there is no negative sign in the numerator. The negative sign is in the denominator, but I have taken that as common. Okay, so now I can cancel out this T and this T. So what is left out is, I can write this as minus of partial V partial T at constant P and if I take this to the numerator, what I'll have here is partial T partial P at constant V, and see I have got dP by dt, so there is no harm in writing this as partial P partial V at constant T. I can write it like this. Sorry, it's not constant T, we said at constant S, right? So I can write this as constant S. We said at S equal to constant. So dP by dV is at constant S. Okay. So what we have here is, now we have got these two terms. And if we remember, which we did before for PVT, so if you can write that equation, partial P partial V at constant T multiplied by partial V partial T at constant P multiplied by partial T partial P at constant V, that is equal to minus 1. Okay. What we already have here is partial T at constant P and partial P at constant V. So these two terms we already have. So if we retain them on one side, so if we take this to the other hand, we'll have minus of partial P at constant P, and there is a minus sign already. So we will end up getting, so let's see what we get. So what we have is Cp by Cv is equal to, we can write this as, so if I just retain this alone on the left hand side, then I can bring this to the right hand side such that this is minus 1 divided by partial P partial V at constant. Okay, so this is what I'll get. So now what we'll have here is, we have partial P divided by partial V at constant S whole divided by partial P partial V at constant T. We have a minus sign, and that has been taken care of by another minus sign here in the replacement. Okay, and we know that this is gamma. And if you remember, we have a definition here for isothermal compressibility. Minus 1 by V partial P at constant T. Okay, dou V by dou P at T. So it is dou V by dou P at T. So what we have here is dou P by dou V. Okay, so the definition for KT is, the definition for KT isothermal compressibility is minus of 1 by V partial V partial P at constant T. We call this as isothermal compressibility. Okay, the same thing, the same result, but if it is at isentropic process, we can call it as isentropic compressibility, and the terms are the same. The only thing is it happens at constant entropy. Okay, so it is called isentropic compressibility. Okay, so now I have partial P partial V at constant S. So if I have a 1 by V term, okay, I can write this as 1 by Ks. And here also I have 1 by V. So for this particular term, we can replace this and write it as isothermal compressibility divided by isentropic compressibility. Kt divided by Ks. Okay, where Kt is isothermal compressibility and Ks is isentropic compressibility. Sometimes they also call it as adiabatic compressibility also. Okay, so for Cp minus Cv, we had a result which is, we had it as Tv beta squared by Kt So for Cp by Cv, we have a result which is Kp divided by Ks. Sometimes this is being asked in a 11-mark question. They ask you to derive an expression for Cp minus Cv and Cp by Cv in terms of these beta, Kt, and Ks values. Okay, so sometimes they ask this. And we have two more portions, and with that, our fourth unit will be completed. One is Joule Kelvin effect. Okay, so in Joule Kelvin effect, see what we do is we are passing a gas, some fluid, through this tube through a valve. And what happens here is a throttling process. A throttling process is something where your enthalpy is constant. Okay, so your enthalpy is constant. There is no change in the energy content of the fluid. So what they do is they identify the value of the pressure and temperature at different points of this throttling process. Okay, so they are finding out by opening the valve, and by opening the valve, they are identifying different pressures and temperatures. Okay, so and by plotting the different values, you are getting the different state points where your enthalpy is constant. Okay, this curve which they have depicted, F1 to F7. Okay, so this is an isenthalp. Isenthalp means just like you have a reversible adiabatic line, here you have an isenthalpic line, which means in this line enthalpy is constant. Okay, it is an isenthalp, but it does not represent a throttling process, which means I am not representing initial value 1 and the final value 2, and I am not drawing a process 1, 2. I am just drawing a curve where enthalpy remains constant at different pressures and temperatures. The pressures and temperatures are varied, but the enthalpy remains constant. Okay, we are not talking about a process, we are talking about the points where the enthalpy remains the same. Okay, so all these processes which they are points, state points which they are denoting, F1, F2, F3, these are states after throttling, and I is the state before throttling. So this is a H equal to constant graph in a TP diagram, temperature versus pressure diagram, and they are calling it as isenthalpic state of a gas. Okay, what is the state of a gas where enthalpy remains constant? What will be the curve when enthalpy remains constant in a TP diagram? That is depicted here. It is not about a process 1, 2. We are not plotting the throttling process here. We are just plotting the points where enthalpy remains constant, and we have joined those points, and it is called an isenthalp. Okay, and if you look at this diagram 11.4, all these diagrams I have taken from PK Nag. If you look at this is one isenthalp. Okay, this is one isenthalp. This is another isenthalp. So you have different constant enthalpy curves. And what they have done is, this is a dotted line which is passing through the maximum temperature point in that graph. If you look at it, this is the maximum temperature point in case of all these isenthalps. Okay, so this is a TP diagram. So the point where your temperature is maximum, so that point is the maxima. So at this particular point, okay, so you are having partial T, partial P. Okay, dt by dp will give you the slope of this curve. These red color curves which I have drawn you, dt by dp will give you the slope of the curve. dt by dp at this point will give you the maxima of that curve. That is why I said the first order derivative will be equal to 0 in case of a maximum. So at this point, at the maximum points, your partial t by partial p will be equal to 0. And if I am able to join all these maximum points, then I get another curve. Okay, and this curve is called the inversion curve. Okay, and they are calling it as mu. Mu is nothing but this partial T by partial P. What is the change in temperature for the corresponding change in pressure? And we said that this is for a constant enthalpy. So your mu is called as Joule Thomson coefficient. It is called as Joule Kelvin coefficient. And Joule Kelvin coefficient is mu. And mu is equal to 0 at all the maxima points. Okay. And if you are able to join all those mu equal to 0 point, that gives you the inversion curve. Okay. And if you look at it, this curve divides the cooling region and the heating region. Okay. To the left of the curve, you have got the cooling region. That means if the curve is moving towards the left, you will end up getting cooled. And if you are moving towards the right, you end up getting heated. Okay. So to the left, you have got cooling region, and to the right, you have got heating region. And this is called as plus mu j, because look at the slope of the curve, it is rising, right? So dt by dp will be positive on this, on the left hand side of the inversion curve. Are you able to see that? The slope of the curve. So if I can show you this green graph, if you see, the curve is actually rising, right? It is a rising curve. So the slope is positive. If you look at the right hand side of the inversion curve, you can see, which I am marking with brown. So here the curve is actually coming down. It is sloping in the downward direction. So the slope is negative. Slope is nothing but partial t divided by partial p, dt by dp. So slope is negative. So you get minus mu j. Okay. J for Joule. Okay. So mu j is Joule Kelvin coefficient, or sometimes they call it as Joule Thomson coefficient also. Okay. So mu j equal to 0 at maximum temperature points. And if mu j is positive, it is the cooling region. And mu j is negative, it is the heating region. Okay. So sometimes, very rarely, maybe in a 2-mark question, they can ask you this. Okay. And this picture I have showed you, because if you take an isenthalpy, if you are taking a constant enthalpy line, say suppose your gas is at the state A, okay, and if you are cooling it maybe, okay, so initially you will have to heat it. So as the curve, if you are if the process is AB, you are actually heating it. Okay, the curve is, you can see that AB is for heating, so you have to go up with a decrease in pressure, and from here to here BC, that will be cooling. Okay, and if you are moving from the state points A to C, you can see that for that the temperature remains constant at both A and at C. Okay. And if you are moving from A to B, the temperature difference is this much, because your temperature T is on the y-axis. Okay. And if you have a process between B and D, there you can see that the temperature difference is maximum. So maximum Kelvin can happen when you are starting the process. So maximum cooling can happen when you start the process at the inversion curve. Okay. So the maximum temperature can drop when you move from the inversion point, which is the maxima point, and from there you move on to point number D. So I think you will be able to appreciate it. Between A and B, this is the temperature difference. Between B and D, the temperature difference is huge, right? So this is the maximum cooling effect that you can have. So that is what they are saying, maximum cooling by Joule Kelvin expansion. Okay, so this is something which you can remember. Okay, so this is Joule Kelvin effect. The next one is Clausius Clayperon equation. So sometimes this is also being asked in, rarely in 11-mark question also. Okay, but it is very simple. Okay, so this Clausius Clayperon equation can be considered for phase change processes like vaporization, when you convert water into vapor, okay, or when you convert a solid directly into vapor, that is sublimation or melting. When you convert a solid into liquid, in all these phase change processes, this Clausius-Clayperon equation can be used. Okay, if you remember, we said we have initially written this S as SF plus X into SFG. And this can also be written in another way. If you expand this, SF plus X into SFG is nothing but SG minus SF. Okay, so what you'll have is SF plus X into SG plus X into SF. Sorry, this is supposed to be minus. So what you'll have is 1 minus X into SF plus X into SG. You can also write it like this. You can either write it as SF plus X into SFG, or you can write it as 1 minus X into SF plus X into SG. Okay. Now what we can do is we can consider the fluid term, which is the liquid. The liquid region, we are representing it as F, and the gaseous region or the vapor region, we are representing it as G. Okay. And in BK now, what they have done is they have replaced this F and G term with I and F. I for the initial liquid condition and F for the final vapor condition. Okay, so if you look at your textbook, in your textbook by BK Nag, he has represented this as 1 minus, just to be familiar, maybe because if the question paper setter follows PK Nag, then he can also represent it like this. So S superscript I for the initial liquid stage, X into S superscript F for the final vapor state. Okay. Similarly, your specific volume can also be written as 1 minus X times V, the initial liquid phase, this is I, plus X into V, the final state, which is the vapor state. So X into V superscript F. And we all know for the phase transition, we use something called latent heat, and it is not sensible heat. Okay. And that latent heat can be represented as L. Okay. And that latent heat can be represented as T times delta S. Because Q is equal to TdS. If you remember, dq can be written as TdS, and if this dq is latent heat, then I write it as L, and this L is nothing but T into S2 minus S1. So in this case, it is T into S final minus S initial. So S superscript F minus S superscript I. I'm just following the same notation as in textbook, so that when you look at the textbook, you will not be confused. Okay, so T times SF minus SI. And if you remember in Maxwell relation, we defined one function called as Gibbs function. Okay, we have not discussed much about the significance of these functions. Okay, and if you have a specific Gibbs function, which means d small g, it can be written as minus s dt plus v dp. Okay, and we can write this as, say, if I am having a process which is a constant pressure process, then I can write this as, so for a constant pressure process, I can write this as S is equal to minus of partial G partial T at constant T. If it is a constant pressure process, then VDP term will be 0. So I can write S as minus of partial G partial T at constant T. Similarly, if I say for a constant temperature process, then I can write this as V equal to partial G partial P at constant T. I can write it like this also. Okay. So why we are doing this is this Gibbs function gives us the change. So there is an SDT, right? So this will give you the change in entropy also. Okay. So that is why we take the Gibbs function. Okay. So a phase change of the first order. It can be known when it satisfies two important conditions which are being prescribed. One condition is if there are changes, there will be changes of entropy and volume. So when you have a phase change process, we have already seen that when we dealt with entropy. So during a phase change process, there is going to be an increase in entropy. Okay, so there will be changes of entropy and there will be changes of volume also. Then number two, the first order derivative of Gibbs function, it changes discontinuously. Those are the 2 points which are given when the phase change takes place, when the phase change of the first order takes place. We are talking about the first order derivative here. So phase change of the first order is known as any phase change that satisfy the following requirements. That is what is given in the textbook. And just reading those statements. So there are changes of entropy and volume, and the first order derivative of the Gibbs function changes discontinuously. Okay. So using the first TDS equation, what was the first TDS equation? The first TDS equation was in terms of CV times dt. So TDS is equal to CV times dt plus P times partial P partial T at constant V into dV. Okay, so this is the first TDS equation. Now I'm going to take three conditions. One is I am saying that the process is reversible. Okay, and then what I say is the process is going to be isothermal, because the phase change happens when the temperature remains constant. At T equal to 0 degrees centigrade, your solid turns into liquid. That happens at 0 degrees centigrade. At 100 degrees centigrade, your liquid turns into vapor. So the phase change process is a constant temperature process. It is also a constant pressure process. Okay, so it is both isothermal as well as isobaric. Okay, so if we consider that as isothermal and isobaric, okay, so the moment I say it is isothermal, this term will become 0. The moment I say isothermal, this term becomes 0. Okay, and so I can write this as T times ds is nothing but S of the final state. This is actually small f, guys, small s, T into SF minus Si. So this is equal to T times dP by dt, and this dV I can write this as Vf minus V initial. All these are small letters, specific volume and specific entropy. Okay, and because the temperature is there on both sides, I can cancel out these two temperature terms. So what is left out is dP by dt. So this dP by dt can be written as SF minus Si whole divided by Vf minus Vi. Okay, and if you can use this relationship, L is nothing but T times SF minus Si, then this SF minus Si can be replaced by L times T. So L is the latent heat of the phase change process divided by the temperature at which the phase change takes place multiplied by the change in volume. P into V of F minus V of I. This is not volume, this is specific volume. Okay, so that is your dP by dt. And this equation is what is called as the Clausius Clayperon equation. So this is nothing but the change in pressure or the change in temperature at the saturated state, which is equal to the latent heat divided by the temperature at which the phase change takes place multiplied by the change in volume. Okay, so this equation is called as the Clausius Clayperon equation. And they also derive the same thing in another way, which is actually this another way using Gibbs function straight away, but there is not much of a difference between this one and that one, so I'm not going into that. There is nothing complicated there, or there is nothing new there. So you can simply remember that dP by dt is L divided by T times change in volume. Okay, between the vapor state, the specific volume at the vapor state minus the specific volume at the liquid state. So that is your Clausius Clayperon equation. Okay, so very rarely they ask problem from this Clausius Clayperon equation also. Okay, one such example you'll solve here, and with that, our fourth unit comes to an end, or fifth unit comes to an end. Okay. Calculate the enthalpy of vaporization of water at 300 degrees centigrade. Use these steam tables for required data. Compare the value obtained with Clausius Clayperon equation. Okay, so if you look at your steam tables for 300 degrees centigrade, so if you have your steam tables nearby, you can check it. For 300 degrees centigrade, the enthalpy of vaporization is nothing but the HFG value. The enthalpy of vaporization is nothing but the HFG value. HFG value is nothing but Hg minus Hf. Okay, so that is the vaporization, right? Vaporization is conversion of water into vapor. Okay, so that the HFG value is 1406 according to the steam tables, which I have in my hand. So HFG is simply 1406 kilojoule per kilogram. Okay, so this is from the steam tables directly. Now they are asking us to find it using the Clausius Clayperon equation also. So just they are asking us to find it in a lengthy procedure. So just now we have seen dP by dt dP by dt is L divided by the temperature into Vf. Vf is Vg and Vi is actually Vf. Okay, so this is the equation and they are asking us to find out the value of L. And the steam tables tells us that this value of L is nothing but 1406 kilojoule per kilogram. So we have to find out the value of L and compare it with this value. Okay, and they have already given the value of temperature as 300. Okay, so for 300 you can check the value of Vg and Vf. So for Vg, what is the value? And for Vf, what is the value? And we are taking these values at 300 degrees centigrade. So if you look at the steam tables, Vf is 0.001404 according to the steam tables. This is 0.001404. Immediately write the units. Most of you are not writing it. This is meter cube per kilogram. Okay. And what is Vg? 0.021649. So this is 0.021649 meter cube per kilogram. Okay, so now what we have is in this equation we have to find out L. We know the value of P, we know the value of Vg minus Vf that is given to us here from the steam tables. What is this dP by dt? That is something which you should take from the steam tables. Okay, so to keep things simple, what is given to us is 300. So let's say T1 equal to say 295, and let's say T2 is equal to 305. Okay, so for this, identify the corresponding saturated pressure values from the steam tables. What is the value of P1 and P2? Okay, so for P1, 295, it is 80.037. So I have old steam tables in my hand, so this value may be slightly different from the steam tables that you have. 80.037 bar, and P2 is 92.144 bar. Now dP by dt is nothing but P2 minus P1 divided by T2 minus T1. Okay, we are just taking this randomly from the steam tables. So this is T2 minus T1. Sorry, in the numerator it is P2. P2 minus P1 divided by P2 minus T1. So if you substitute these values, you'll get some answer in bar. In the numerator you have bar, and in the denominator you have got degree centigrade. So your dP by dt is bar per degree centigrade. You can also call bar per Kelvin. Nothing wrong. Okay, but you have to be very careful here. This T should be substituted in Kelvin. Difference, no problem. You can 305 minus 295 degrees centigrade is also 10. If you convert it to Kelvin and then subtract also, you'll get 10. Okay, so temperature difference, that is not a problem, but when you substitute temperatures separately, you should substitute it in Kelvin. So 300 plus 273, it should be 573. Okay, and let's see what answer the book value gives us. Okay, so these are the values. So actually the steam tables which the book they have referred to, the HFG value is 1404.9. For me, it was 1406. The actual HFG value is 1404.9. And if you look at it, they taken 295 and 305. Okay, and they have found out dP by dt values or partial B by partial T values. And they have got the value in bar per degree centigrade. They have substituted it. HFG is dP by dt into T into VFG. T is 573, VFG, they have subtracted Vg minus Vf, and they are able to get 1404.6. The book answer was the steam table value was 1404.9. So it is very close. Okay. And you can try checking with a different value. If you can read, instead of 295, try this with 290. And replace this T2 with 310. Increase the gap and see how it turns out. So in that case, your accuracy will come down. You won't get 1404.6. It will be lesser than 1404.6. So the minimum variation in the pressure, the difference that you have, you will be able to get a good accurate value. So you can try that by replacing a different value for T1 and T2. You can try and see what value you get. Okay. So with this, we come to the end of the fourth unit.
So we have to take the temperatures randomly, sir.
Yes, randomly.
Okay, sir.
So first it is given as 300 degrees centigrade. I have taken it as 295 and 305. You can take it as 290 and 310 or 280 and 320. Either way you can take it.
Okay, sir.
Okay. So with this, we come to the conclusion of the fourth unit.